The final topic in our study of kinematics is projectile motion. Now, a projectile is any object that moves unpowered through the air. Most of the time, that means something like a ball as opposed to something like a rocket or a helicopter or a plane, because those things have forces that are pushing them or pulling them through the air, whereas a ball does not. The path that an object takes as it's going through projectile motion is often called a trajectory. And the key idea for projectile motion is that the only force that acts on the object is gravity. That means that the object is really only experiencing one type of acceleration, and that is downward at negative 9.8 meters per second squared, or negative 32 feet per second squared. There's a couple terms that we need when we're studying projectile motion. First of all, the hang time of an object is the amount of time that an object is in the air. Typically, we don't know this ahead of time, and we need to calculate this. And we do it by using a vertical position formula, and we set that equal to 0. Remember, that would be because the final vertical position of an object when it hits the ground would have to be 0. Another term that's often used is the range. The range is the distance that the object travels before it first hits the ground. This does not count things like bounces or rolling. Usually, to calculate this, we need the hang time, and we plug that into a horizontal position formula. Another term that's often useful for us is to find the maximum height. The maximum height of an object always occurs when its vertical velocity is 0. Remember, that's that split second of time where an object has reached its maximum height and it isn't going up any higher, nor is it coming down quite yet, so its vertical velocity is 0. Usually we find that time first, and then we plug that time into the vertical position formula to figure out what is the maximum height. Alternatively, you could look at a graph and see where does it reach a maximum height. Now let's look at a practical example. Suppose a baseball gets hit, and it's hit at an angle of 23 degrees above horizontal at 110 feet per second. Let's see if we can calculate not only where does it hit the ground, but how long, that is, how much time it takes for the outfielder to perhaps get in position to make a play. Typically in a projectile motion question, when you're calculating the range, you really need to find the time that the object is in the air first, and then use that in a horizontal position formula to calculate how far the ball travels. But before we do anything, let's start to fill in the quantities that we know. The only thing we're told specifically is the initial speed and the fact that that was at an angle. The initial speed was given to us at 110 feet per second, and that's an angle of 23 degrees above horizontal. Typically, it's useful to draw a triangle here and to find the components of this velocity. So we'll put 110 as the combined velocity and 23 degrees as our angle. Now we can break this initial velocity into how much of it is horizontal and how much of it is vertical by using sine and cosine. Remember, we can find this by taking the hypotenuse, 110, and multiplying it by the sine and cosine of 23. I don't always remember which is which, but it's going to be fairly obvious when we look at the numbers which one is the shorter vertical velocity and which one is the longer, bigger horizontal velocity. If we type in 110 times the sine of 23 degrees, and then I'm going to hit second enter and change that to a cosine of 23 degrees. It's obvious that the cosine must have been the horizontal velocity of 101 or so, and the vertical velocity must have been the smaller 43. Let's transfer those numbers into our chart. The horizontal was 101 meters per second, and the vertical we said was 43. The rest of these quantities we need to find by making a few assumptions. First of all, we assumed that this is a projectile, meaning it has no other forces acting on it except gravity. Therefore, its only acceleration is downward at the typical rate of gravity, which for feet per second squared is negative 32. Horizontally, we are going to assume that there is no acceleration. That is, there's no winds involved, there's no rocket on the back of the baseball, and there's no air friction. The final velocities for this particular question are irrelevant. We don't need to know how fast the ball is going when it hits the ground. Horizontally, we're going to assume that the initial position is 0, and then the final position will be the distance that the ball travels. Vertically, I don't want to say the initial position is 0, because that would mean the baseball was hit off of the ground like a golf ball. It was probably a couple feet up in the air, let's say 2 feet. Final position vertically is definitely on the ground. We'll call that 0. Unless we want to consider the possibility that an outfielder catches it, in which case the final position might be a little higher, say 5 or 6 feet off of the ground. Let's keep it simple and just calculate when it hits the ground. To calculate when it hits the ground, we use the vertical numbers and the vertical position formula and solve that for t. Vertically, the position formula is the same one we've been using all along. And we'll plug in vertical numbers. Or the final height is 0. The initial height is 2. The initial velocity is 43. And time is an unknown. That's a variable. Plus 1/2 times negative 32 times t squared. And this equation, because it has both a t squared and a t in it, is not going to be a very easy one to solve. I think we should use the quadratic formula here. If we do that, then this is our a value, this is our b value, and this number that's not by a variable at all would be our c value. Let's use our program to calculate that. We'll go to Program and Quadratic Formula. The a value is, and feel free to just type in half of negative 32, although you could probably have just written negative 16, and that would have been fine too. The initial velocity is 43, and the initial position was 2. So we get 2 values for time. The first value for time is a negative number. That doesn't make sense. The second value for time is the time that we're looking at. That's how much time this ball was in the air before it hit the ground, 2.7 seconds. The second question is, how far does the ball travel before it hits the ground? To find that, we're going to use the time that we just calculated and a horizontal position formula. We'll use the exact same formula, but this time we're going to plug in only the horizontal numbers. The final position is the thing that we don't know. The initial position is 0. That term we can neglect. The initial velocity is 101 times 2.7 seconds. And we assumed there was no horizontal acceleration, so we can cancel that term off. And it's very simple. Our final position is just 101 times 2.7 seconds, or about 272 feet. In most ballparks, that would not quite be a home run, but be pretty deep. Let's quickly make a graph of this on our calculator. And if you already know how to do this, you don't need to watch anymore. You can sign off. Have a great day. To make a graph of this on our calculator, we're going to go to the y= screen and type in horizontal and vertical position formulas. Remember that I'm in parametric mode. So horizontally, the initial position is 0 plus, and here I'm going to do something a little different. Rather than type in 101, I'm going to type in 110 times the cosine of 23. That's our initial velocity times time, plus 1/2 times 0, because there's no horizontal acceleration, times t squared. Vertically, we'll do the same thing. There is an initial position, so we'll say 2 plus, and I'm going to use 110 times the sine of 23 times t plus 1/2 of negative 32 t squared. And those will be the equations that we need. A quick check of the window settings. 0 to 3 seconds should be okay. We calculated that the hang time is about 2.7. Horizontally, let's suppose our ballpark is 300 feet. So we'll go from 0 to 300 by, I don't know, maybe 25. And vertically, let's say, I don't know, 0 to 50 by 5. That should give us a fairly square-looking graph. I must have an error somewhere. We'll hit go to. I forgot my 1. Second, insert 1, and graph. So there's a picture of our baseball's flight. Now that does not look very true to scale because it left the bat at 23 degrees, which is really flat. In order to make this more square, we should hit zoom and zoom square. What that'll do is it'll keep our x-axis the same, but it will shrink the y-axis to be the right shape so that our picture looks realistic. There. That graph looks a lot flatter, a little bit more realistic. Now if we went to the y equals screen, we could quickly alter a few things and see what happens. Specifically, let's say the baseball was hit a little bit higher, say 33 degrees. Would that make the baseball travel farther? Let's find out. Change both angles to 33 and regraph. Notice how the baseball stops mid-flight. That's not because it all of a sudden exploded. That's because our time setting only graphed the first 3 seconds of the flight. So this baseball must be in the air for longer than 3 seconds. If we go to our window settings and change this to, say, 4 and regraph, now we should see the whole thing. And if our baseball field is exactly 300 feet long, then this does look like it is indeed a home run.